So today we're going to talk a little bit about a new idea. But before we get started, I just want to show you this one. It's not the exact car, but it's the same model and same year and about the same condition. This is my first car in Hong Kong. It was an interesting buy. It was about $1,000 used. It didn't have as much rust as it had here. It did have holes in the bottom, but the very first time I took it downtown, everything went well until I tried to go back home again. For those of you who don't know Hong Kong, it's a very mountainous island. And so, coming up the first mountain, head back home, I gunned it, of course, before I got to the base of the mountain and started going up. And with my foot all the way to the floor, climbing the mountain, I just kept going slower and slower and slower until finally I came to a complete stop with my engine revving full blast and a line of cars behind me, single lane, honking their horns as I very embarrassingly and sheepishly opened my driver's side door, stuck my foot to the ground, held the pedal down with my other foot, and pushed myself to the side of the road using my foot while I had the engine revving. I soon discovered as long as I turned off the air conditioning and floored it, I could make it up the mountain. But it was an embarrassing first trial. So, if you're thinking about Christmas presents, we'll talk about this a little bit. A very low power car. If you're thinking about Christmas presents, here it is. I prefer red. This Lamborghini, much nicer car, but it's about 800,000 US dollars. So here's the question. Both could go 100 kilometers per hour or 60 miles per hour, the legal speed limit, and they both had about the same mass. So my question is, which one had more kinetic energy if you're going 60 miles an hour or 100 kilometers per hour? And if you think about kinetic energy, 1/2 mv squared, the answer is exactly the same. So then the question is, and I may have given you a hint already, why spend the extra $800,000 besides the obvious fact that it has style and air conditioning that even work while you're going uphill? And you can probably guess just based upon the answers I wrote down over here. My car, that car, on level ground, you held the pedal down, and it took about a minute to get up to 60 miles an hour. It was embarrassing. The Lamborghini, about 3.3 seconds. Yes, I know the Teslas, some of them have even more horsepower than this, can do it in shorter time, but this one's cool. What's the difference here? The answer is the amount of power that the engine has. Power is defined as the rate at which energy is produced or consumed. Notice the key here is rate. So it's defined as this. It's the change in the energy divided by the change in time. In fact, I sort of like writing it this way. Power, represented capital P, is the change in the energy of an object over the change in its time. And the units for it are joules, because energy is measured in joules, and time in seconds. So joules per second, or watts, abbreviated just with a capital W. You've actually seen it quite a bit. For example, light bulbs are rated in watts. The 40-watt bulbs that most classrooms have use 40 joules of energy every second they're turned on. So how much energy, or how many joules of energy does it use in 60 seconds? Well, it'd be 60 times 40, or 2,400 joules of energy. It's that simple. You can work it out. Every electrical device you have at your home has a certain power rating on it. It tells you how many watts, that is, how many joules of energy it uses every second it's turned on. I do need to mention this just real quick because there is an older unit of power besides the watt. It's the horsepower. And it's a simple conversion. You'll still see horsepower written on lawnmower engines, sometimes on new car engines. It was determined by measuring the output of a standard quarter horse during an 8-hour day. And it turns out, on average, a quarter horse could produce 746 joules of energy every second during an 8-hour day, which is pretty amazing.
Hey, Doc, this is it.
Never mind that. Never mind that now. Never mind that. Never mind.
Why, that's me. Look at me. I'm an old man.
I'm Dr. Emmett Brown. I'm standing here on the parking lot at
Thank God I've still got my hair.
October 26th.
What on earth is this thing I'm wearing?
18
Wow, this is a radiation suit.
Radiation suit. Of course. Because of all the fallout from the atomic wars. This is truly amazing. A portable television studio. No wonder your president has to be an actor. He's got to look good on television.
Whoa, this is it. This is the part coming up, Doc.
No. This sucker's electrical. But I need a nuclear reaction to generate the 1.21 gigawatts of
What
electricity.
did I just say?
Flux capacitor stores. This sucker's electrical. But I need a nuclear reaction to generate the 1.21 gigawatts of electricity.
1.21 gigawatts! 1.21 gigawatts! Great Scott!
What the hell is a gigawatt?
How could I have been so careless? 1.21 gigawatts! Tom, how am I going to generate that kind of power? It can't be done, can it?
Doc, look. All we need is a little plutonium.
Oh, I'm sure that in 1985, plutonium was available in every corner drugstore, but in 1955, it's a little hard to come by. Marty, I'm sorry, but I'm afraid you're stuck here.
Whoa, Doc, stuck here. I can't be stuck here. I got a life in 1985. I got a girl.
Is she pretty?
Doc, she's beautiful. She's crazy about me. Look at this. Look what you wrote here, Doc. I mean, that says it all. Doc, you're my only hope.
Marty, I'm sorry, but the only power source capable of generating 1.21 gigawatts of electricity is a bolt of lightning.
What did you say?
A bolt of lightning. Unfortunately, you never know when or where it's ever going to strike.
We do now.
If you didn't realize it already, that was Back to the Future in 1985. I love the fact that Emmett Brown pronounces it 1.21 gigawatts. I'm going to put it in parentheses. What was he talking about? He's talking about a unit of power. What he meant to say was gigawatts. That's billions of watts. But they left it in the script even afterwards. Yeah, it should have been gigawatts, but it's doggone cool. In it, if you haven't seen the movie, it's a classic. They use a bolt lightning to actually send Marty back to 1985. But here's the interesting part. I think they really meant to talk about gigajoules of energy, which would be a large amount. Here's the interesting part. It turns out an ordinary AA battery, like the ones you buy at a grocery store, can release about 15,000 joules of energy. If it could be stored and released quickly, it could supply the 1.21 gigawatts that the time machine needed. So 1.21 gigawatts, 10 to the ninth, take that divided by time. If you could release the energy in the battery in a very short time, yeah, in this case, this amount of time, it would actually produce that amount of power necessary to actually do it. Please make sure in your mind you have the difference between energy and power. Power is the amount of energy delivered per unit time or used per unit time. It's not energy itself. Normally at this point, I actually get a couple of students to actually run up the stairs. The interesting thing about this, you can either do it indoors or we can do it outdoors on there. Given the height, we oftentimes get answers on this, which will actually be larger than 746 watts. And I'm going, wait a second, these people have more power than a horse? Again, remember, 1 horsepower is that. What's going on? How is that even possible? How could anybody have more power than a horse? The answer is we can produce that rate of energy production for a few seconds. A standard quarter horse, the way it's defined originally, could do it for an entire 8-hour day. That makes a huge difference. I just want to do a couple quick examples. I already have one formula on the bottom there. A 1,500 kilogram car has a 120 horsepower engine. Again, horsepower, older unit, conversions down at the bottom right. What's the power output of the engine in watts? Whenever you have horsepower immediately converted into watts, so our power is 120 horsepower. The conversion, 746 watts for each horsepower, gives us 89,500 watts to 3 sig figs. The next question is, all right, what's the energy output of the engine if it runs at full power for 15 seconds? Well, given our definition of power, we can just plug in what we know. We know the power is 89,500 watts. The time is 15 seconds. And if you solve the energy, you end up with this rather large value of 1,340,000 joules, again to 3 sig figs. Last question, what will be the car's velocity at the end of 15 seconds if it starts from rest and all of the energy is converted into kinetic energy? So kinetic energy, I already have the formula down below, is 1/2 mv squared. So what are we going to do here? We're going to take all that energy and set it equal to that. If we do that, we end up with this, plugging in the mass of the car, 1,500 kilograms. Doing a little bit of math, we get that. And then finally, we get that, which is about 92 miles per hour, which is faster than this car with this rather low power engine could actually do. Again, just a quick note on this one. This answer is actually too large because real vehicles always generate some e-dis, some heat as they convert the gasoline and the power output of the engine into actually motion. Heat in the transmission, heat in the drivetrain, all along the way. It's not 100% efficient. A couple other quick examples. When we talk about power, the energy we have here at the top here can be any form that we've talked about. And we have 4 forms of energy. We've got work, gravitational potential, kinetic, and elastic potential energy, or energy stored in a spring. In this case, an 1,800 kilogram elevator is lifted 14.7 meters in 7.1 seconds. What's the power output of the engine? Again, power is energy over time. What kind of energy is the elevator gaining? Well, in this case, it is gravitational potential energy, MGH. Over the time, we're going to have that divided by that amount of seconds. I'm doing gravity as 10. And you'll discover that the power output of the motor is about 37,300 watts. It's another example. A 1,000 kilogram car starts from rest and achieves a speed of 30 meters per second. That's about 60 miles an hour in 6 seconds. What's the power output of the engine? In this case, same equation, but what kind of energy are we gaining this time? The answer is kinetic energy, the energy of motion. Plugging in our numbers, we'll discover that the engine's power output is about 75,000 watts. And yes, you could convert that to horsepower if you wanted to. Lastly, a person slides a 100 kilogram crate at a constant velocity through a distance of 10 meters in 20 seconds. If the coefficient of kinetic friction, mu sub k, is 0.1, what was the power output of the person? Well, drawing it real quick, force of gravity, 1,000 newtons, normal force, 1,000 newtons. Solving then for the force of kinetic friction, it would be 1/10 of that, or 100 newtons, which means to keep this thing moving at a constant rate, you'd have to apply a force of 100 newtons this way to keep it sliding at a constant rate. Well, what kind of energy are we talking about now? We're not changing our kinetic, we're not changing our gravitational, we're not changing elastic, we're not compressing a spring or stretching a spring. What kind of energy are we dealing with this time? The answer is work. Again, remember, work is a form of energy, and we're talking about the amount of work that we do. In this case, the person's applying 100 newtons through a distance of 10 meters in 20 seconds. And the angle between the displacement and the force is 0 degrees. So we're talking about cosine of 0. If we solve this one, we'll discover the person's output is about 50 watts. And you're like, okay, got this. One more example on this one. This is a picture of my nephew when he was young on a ski hill. This is not without a chair lift. It had one of those rope lifts. If you haven't used it before, you grab the rope and it takes you to the top. He was about 40 kilograms then. Now he is a sophomore at university, and he's 6'7". Yes, I have to look up to him. In this case, the skier's initial velocity was 0 before he grabbed onto the rope. Final velocity was 2 meters per second. That's how fast the rope was moving. And he goes up a 50-meter tall hill in 32 seconds. What was the power output of the motor required to lift one skier? Again, we're talking about energy over time. But in this case, what kind of energy did the skier gain? The answer is both gravitational potential energy, mgh, and kinetic energy, 1/2 mv squared. Start out at 0, ended up at 2. So in this case, plugging in our numbers, again, the mass of our person is 40. The height of the hill was 50, and the velocity they gained was 2, all in 32 seconds. Solving this one, notice that the increase in kinetic energy is relatively tiny compared to the change in gravitational potential. It turns out it took almost no energy to get the skier moving. It took a lot more energy to lift them up the hill. If you solve this, you'll discover it takes about 630 watts for each skier that's on that rope. So if you had 10 skiers, it would be 10 times that. Or that's how many horsepower it is, if you're curious, just dividing by 746 watts. My last bit is I want to introduce a special equation. Remember in the previous example, we had an example where the change of energy was the work done. Force times displacement times the cosine angle between those two. But I want you to notice something. You've got delta x over delta t, displacement over time, which means you can rewrite this equation just like this. This is a special case for power, and it's used quite a bit for people who design race cars or boats or airplanes or jets, anything that involves a frictional drag force. And let me give you a quick example. Here's a small fishing boat with a 20 horsepower trawling motor. And let's say that the water resistance is producing a constant drag force of 500 newtons. If the boat is now going forward, it means it must be producing 5,000 newtons forward, or the engine's producing that much thrust. How fast can this boat go? That's the question. So velocity is going to be in the same direction as the force or the thrust the engine's producing. In this case, we're going to use this equation. The power, we've got to convert it in from horsepower to watts, just using the simple conversion. The force is going to be 5,000. The angle is going to be 0 degrees between the velocity and that force. And we're going to solve for the velocity. And if you do this and run the numbers, you'll discover that the fastest this trawling boat can go is about 3 meters per second, or about 6 miles per hour. Just enough for a trawling motor, it really can't go very fast. Now, I need to mention one thing before we leave this problem. The idea that the drag force is actually a constant value is actually sort of imaginary. As things go faster, the drag force typically increases on them. It's not a constant value. So I made this kind of an artificial problem just to make it a little bit easier. Here's a more realistic problem. In this case, most car manufacturers will put a car into a wind tunnel and discover what the coefficient or drag coefficient is. In this case, the force of air drag on this car depends on its velocity. The force is given by 0.2 times v squared. And I know I didn't put units on the 0.2, but I didn't want to make this too confusing. So now I can actually ask the question. If we find out that the force of air drag is given by that equation, how fast can a 135 horsepower sports car go? What's its maximum speed? So in this case, using the same equation, power is equal to force times velocity times the cosine of the angle. In this case, again, my power is now given by this. I'm just converting that into watts. The force we're going to use in just a second, times velocity times the cosine, all those kind of fun things. But in this case, the force is going to be given by this expression right here. So if we plug that in, what do we get? Well, we get this. The force is given by this. Our velocity is unknown. The angle between the velocity and the force, in this case the force that the engine has to produce, is going to be 0 degrees. And so we can actually solve this. You'll end up with a cubed root in this one. Whoa! And I actually didn't put the answer down on this slide, so give me a quick second. So 100,000, 710 divided by 0.2, and then that answer raised to the 1/3 power. We get a final velocity of, for all practical purposes, about 80 meters per second to 2 sig figs. That's about 160 miles per hour. Again, assuming no air drag or no losses in the drivetrain. That's pretty doggone fast. All right. As we're talking about power, I do need to mention this. You know that we use a lot of electricity, both at home and at school. And we're charged for the number of kilowatt hours we use each month. And technically that's kilowatt times hours, but it's written like this. Rarely do they put the little dot in between. Just kW, kilowatts, times hours. My question is kilowatt hours a unit of energy or is it a unit of power? Be careful on this one. If you remember power is energy over time, if you multiply both sides by time, you end up with energy. Kilowatts, 1,000 watts, is a unit of power. An hour is a unit of time. Not seconds, our normal one, but you get the idea. So a kilowatt hour is power times time. Oh, power times time, what is it? It actually is a unit of energy. So you actually don't get charged for the rate at which you use electrical power, but the total amount of electrical energy you use each month. If you do a little bit of calculations on this, 1 kilowatt is 1,000 watts. 1 hour is 3,600 seconds, 60 times 60. And so 1 kilowatt hour is equal to 3,600,000 joules. And yes, that is a unit of energy. Should you memorize this one? No, but it is useful to know. In fact, it's going to be useful for one of your homework problems tonight. Take a look at this. Talking about your homework tonight, here's a worksheet, or the one that's assigned for night on power. I'm not sure if it's 5 or 4. Hulky and Bulky are 2 workers being considered for a job at the UPS loading dock. Hulky boasts that he can lift a 100-kilogram box 2 meters vertically in 3 seconds. Bulky counters with his claim of lifting a 200-kilogram box 5 meters vertically in 20 seconds. The question is, which worker has a greater power rating? So, power, energy over time. In this case, what kind of energy is Hulky dealing with? The answer is he's increasing the gravitational potential energy of that crate. Plugging in the numbers, he's lifting a 100-kilogram crate a distance of 2 meters. And so there's my 2 meters, that's my 100 kilograms, gravity's 10, in 3 seconds, which I'm putting down here. And if you work it out to 2 sig figs, Hulky's power output is 670 watts. So what about Bulky? Well, Bulky's also going through, or lifting a thing, so it's undergoing gravitational potential energy change. In this case, though, he's lifting a 200 kilogram crate, a total of 5 meters, gravity's still 10, but in a time of 20 seconds. If you work that out, that's 500 watts. Who has the greater power rating? The answer is, it's Hulky at 670 watts. The other worksheet problem is this one, number 7 I want to do with you. Your electric company sends you a monthly bill informing you of the number of kilowatt hours you've used that month. Are they charging you for energy or power? Explain. Best explanation, again, is just running it through like we did just a moment ago. A kilowatt hour is equal to this many joules, and joules is a form of energy. That's a good explanation. And now, how many joules does your 1600 watt blow dryer transfer if you dry your hair for 5 minutes a day, every day for 30 days? And then there's a second question, how much will it cost if 1 kilowatt of electricity is 32 cents? Well, first of all, figure out the energy. We've got power and we're looking for energy, so I'm going to use this same equation we did or used up above here. I just reversed it, actually. It comes from the definition of power. In this case, the power output of the hairdryer is that. And then just some conversions. We need that. You figure out how many seconds we used it. 5 minutes per day. You could do 60 seconds per minute times 30 days. And if you do that, you'll discover that you're going to use a total of 14,400,000 joules to 3 sig figs. That's a lot of energy. How much is it going to cost you? Well, again, we can convert that into the number of kilowatt hours we used. Remember, 1 kilowatt hour is equal to 3,600,000 joules. That's what we got from up above here. And so if you work that out, it's going to use exactly 4 kilowatt hours. So how much is that going to cost us? Well, now it's pretty simple. 4 kilowatt hours is going to be 32 cents per kilowatt hour, which gives us our total cost of $1.28. 32 cents is currently the average price in California for a kilowatt hour. It's still incredibly reasonable. It's actually not too expensive, even if you use a fairly large device for a significant amount of time every day. And that is it. Good luck with your homework tonight. Have fun with it. Help each other if you need it. And I'll